Hello engineers! Today we're going to figure out how a strobe light works, and then we are going to build our very own from scratch. You're watching Blueprint. Strobe lights, of course, flash at a known frequency, usually less than 10 Hz. There's more than one way to make this happen. Let's take a look at one. Most consumer strobe lights look something like this. Though more modern ones will use LEDs, this older one uses an incandescent filament, a lot like a camera flash. Of course, the problem with that is that incandescent filaments will heat up a lot faster and will also burn out relatively fast. That's why these filaments are largely being phased out and replaced with LEDs. Now of course if we plug it in, we will see it flash, except this one barely works anymore, and its frequency is, well, pretty pitiful. On the back we have our 120 or 240 volt input, and a knob that adjusts the frequency of the flashes, although the range is fairly limited. We also see warnings telling us not to open the case or risk electrical shock. We're enlightened engineers, so we're gonna go ahead and ignore that. Here we go. Now let's follow some of the traces. First of all, the 120 volt input is here in the back. Now it's filtered into a... Whoa! What the? If unlike me you're not a total idiot, your first step will be to unplug whatever you're working on. Here's a closer look inside this strobe light. After the 120 volt input near this charge section, the power is rectified using a bridge rectifier made up of these 4 diodes here. For the actual filament circuit, it's actually pretty simple. It uses an RC circuit. These here are very large capacitors, and this is a power resistor. And this is also tied into the potentiometer knob in the back where you adjust the frequency. That's because in RC circuit, the time constant is equal to the resistance times the capacitance. And these capacitors will hold up a very large charge and release it through the filament all at once, getting a very large current and causing it to flash very quickly. Now see, I can do the same thing if I just tap my power supply across it. Or maybe not. That's unfortunate, but I wasn't going to use this anyway. I just wanted to show you how it worked. What we're going to use is a more modern and adjustable 555 timer, which can be used for monostable and astable timing circuits, as well as an LED chip, which I went over in a previous video. Let's go ahead and assemble our oscillator. What we're going to use is an NE555 timer. Now this has 2 modes, astable and monostable. The difference is that in astable oscillation, you can set different periods for the amount of time spent high and the amount of time spent low. Both of these circuit diagrams and more can be found on the LM555 datasheet, which I'll link in the description. So I'm going to take the 555 timer and straddle it across this center line like this. The notch on the left side of the integrated circuit represents the directionality. The bottom left pin is pin 1 and the upper left pin is pin 8, and the pins increase, snaking around like this. Pin 8 is VCC in, so we're going to go ahead and hook up a connector between pin 8 and the positive power rail. Likewise, pin 1 is ground, so we're going to hook up a jumper from pin 1 to the ground rail. Pins 7 and 6 control the timing. This is done using a pair of resistors and a capacitor. I decided to make RA a 10 kilo ohm resistor, RB a 470 kilo ohm resistor, and my capacitor a 0.47 microfarad capacitor. Therefore, I will have a frequency of about 3 Hz. If we want to be able to vary our output, what we can use is a potentiometer. Potentiometers are essentially variable resistors. The knob controls a wiper that moves across a resistive surface. First I'm going to connect the 10 kilo ohm resistor across pins 8 and 7. Then I'm going to connect the 470 kilo ohm resistor between pins 7 and 6. Then I will connect the 0.47 microfarad capacitor between pin 6 and ground. Also on pin 6, we're going to make a jumper connection between pin 6 and pin 2. Pin 5 we can just go ahead and leave open. Now pin 4 we're going to also make a jump between pin 4 and the positive power rail. And finally, pin 3 is our output. This LED chip, as you might remember from one of my previous videos, can get pretty bright. In fact, it has a forward voltage that's relatively high, around 23-24 volts. And at 30 volts it can get quite intense. Now since I already have this frequency for my 555 timer, my natural inclination is just to take some lead wires and hook it up in series with the 555 timer. And then turn the voltage up to about 30. Well, my 555 timer just exploded. I guess it can't handle that high of a voltage. After looking back at the data sheet, I realized that the 555 timers can only handle a maximum of 18 volts and about 1/4 of an amp, which would never be enough to power a big kahuna like this LED. The solution around that is, instead of having all the current sink through the 555 timer, the 555 timer can gate this MOSFET, an IRF 540N, which can handle 100 volts and 33 amps. So we're going to take our IRF 540N and we're going to put it into the breadboard. And then we're going to take the signal coming from the 555 timer and we're going to run it through this resistor. The resistor is to limit the current and make sure at the base of the transistor isn't getting too much current through it. What I want to do is I want to have the source go through the LED, so I'm going to leave this wire open. That's going to hook up to the LED chip later. And I'm going to have the drain go from the 3rd pin to ground. By the way, before I forget to mention, this is a 300 ohm resistor. Since my power supply is going to be set between 25 and 30 volts, I made this voltage divider so that to the 555 timer I can still get about 10 volts. This is a 10 ohm resistor and this is a 22 ohm resistor, which means that the voltage in the center is approximately 1/3 of the input voltage. Okay, well, that was doomed to fail. You see, the current draw through the resistors is way higher than their 1/4 watt rating. So instead I just used an LM7812 12 volt regulator. For reference, the pin configuration is power input, ground, and power output. So now, as you can see on the oscilloscope, as I raise the voltage past 12 volts, it'll stop increasing as the voltage gets higher. So now I have enough voltage to power my 100 watt LED, and this is still capped at 12 volts on the 555 timer. So here is a look at my final schematic. It includes everything that is working on this final prototype board. Alright, I've built, destroyed, and built again this circuit. Now is the moment of truth. Yes! If my calculations and construction are correct, this should be blinking at 3 Hz and it should spend the same amount of time on as it does off. And actually, this isn't even at the maximum power I can supply to it. The maximum power would be something like this. Remember, to make it blink faster, all you need to do is replace RB in the 555 timing circuit. It's like magic! Remember, it's all fun and games until somebody has a seizure. I hope that you now know everything you need to know to make any kind of strobe light that you want. There are also documents in the description for you to review for more information. And of course, you can ask me anything you want in the comments. If you made it this far, I suspect you enjoyed my presentation, so go ahead and tell me by hitting the like button below. And if you didn't, well, what are you still doing here? Subscribe for more content, and thanks for watching.